Hey everyone, and welcome to The Explainer. Today we're zeroing in on a massive breakthrough that is fundamentally reshaping edge computing in 2026. We're talking about the cutting-edge YOLOv11 AIIT architecture. We are going to explore how this specific technology has evolved way beyond just, identifying objects on a screen to actually driving physical autonomous AI out in the real world. Okay, let's dive into this. How do you spot a target that takes up less than 0.1% of a 4K image in real time without literally melting a drone's processor? Because honestly, that is the high-stakes physical constraint of autonomous robotics today. It is one thing to run a massive AI model in a nice, cool, temperature-controlled server farm, but it's an entirely different beast to process ultra-high-resolution panoramic video on a tiny little chip strapped to a drone surveying a desert, or on a robotic arm moving at lightning speed on a factory floor. So here's our quick roadmap for today. We'll start with the Vision AI paradigm shift, then look inside the AEIT architecture and unlock NPU edge performance. From there, we'll cover real-world business applications, securing agentic AI systems, and finally wrap up with the ethics of physical AI. All right, Section 1, the Vision AI paradigm shift, moving from general-purpose detection to specialized edge attention. It's crazy how fast the AI landscape has accelerated. Back in 2023, YOLOv8 was making huge waves by introducing a split and merge strategy, right? But it created these annoying bottlenecks when trying to capture long-range global context in an image. Then, by 2025, YOLOv10 totally eliminated massive latency by achieving NMS-free training, which essentially meant the AI didn't have to waste time filtering out redundant, overlapping boxes anymore. But 2026, that is the real paradigm shift. We've jumped straight into the lightning-fast YOLOv11 AIT framework. It pioneers this transformer-inspired edge perception that perfectly balances high-resolution sensitivity with true real-time speed. Moving to Section 2, inside the AEIT architecture and how it solves the quadratic complexity problem. To truly grasp the immense power of this model, we have to look under the hood. For a long time, standard vision transformers were the absolute gold standard for image analysis. But they had a fatal flaw when it came to edge devices. Their computational complexity is ON squared, where n is the number of pixels. This dreaded formula basically means that as your image resolution goes up, say you're using a 4K drone camera, the math required to process it grows exponentially. It goes off the charts. If you tried to run older transformer models with that much data on the edge, you would literally overheat and melt the drone's processor. And this brilliantly illustrates the solution. The YOLOv11 AIIT framework swaps out that traditional backbone for something called efficient VIT. So instead of doing all that incredibly heavy quadratic math, it approximates the attention mechanism with a linear feature map by computing the values in a different order, specifically leveraging the associative property of matrix multiplication. The whole operation becomes linear. It keeps the hardware cool, and it keeps the processing unbelievably fast. So what exactly does that mean? Well, by definition, linear attention replaces the computationally heavy softmax calculation with a much lighter ReLU-based global attention mechanism. This right here is the secret sauce. It reduces the complexity from quadratic down to linear. But, and this is absolutely crucial, it still preserves the AI's ability to see the global receptive field. In plain English, it allows these drones to process massive 4K panoramic images without stuttering, lagging, or crashing. Let's look at how this builds into the most sophisticated part of the architecture, the hybrid attention strategy. The AI is actually alternating between two mechanisms. First up is local window attention, or LWA. This partitions the image into these tiny 4x4 pixel grids, allowing the model to precisely capture microscale textures. Think about trying to distinguish the subtle dirt edge of a plateau pika burrow from just regular surrounding soil. But if you only ever look at tiny windows, you become short-sighted, right? So it pairs that with dilated global attention, or DGA. Using a dilation rate of 2, DGA scans a sparse grid across the entire image. The contrast between these two mechanisms is brilliant. The AI perfectly balances this intense focus on tiny subpixel defects while never losing sight of the big picture, which totally prevents what developers call information dilution. Okay, Section 3, unlocking NPU edge performance and hitting that vital 33 millisecond window. Now, what's really interesting about this slide is that software algorithms are really only half the battle. When we shift these workloads from a traditional CPU over to a physical neural processing unit, or NPU, using INT8 quantization, the results are just staggering. I mean, look at the power consumption. It drops from 12 watts down to just 5 to 7.4 watts. And the latency, it plummets from taking over a full second down to between 4 and 33 milliseconds. That 33 millisecond window is basically the holy grail here, because it means the AI is processing at 30 frames per second. It is officially real time. But on top-tier NPUs like the Rockchip RK3588, we aren't just hitting 30. We're hitting 244. That is 244 frames per second. That massive number really hammers home what real-time speed actually looks like in practice. Because by offloading all this heavy lifting to the NPU, we reclaim so much overhead from the CPU, giving the overall system the actual headroom necessary to control the robotics or safely fly the drone. Section 4. Real-world business applications. Moving from reactive monitoring to proactive automation. Let's shift away from the micro-level hardware for a second and look at the macro-level factory floor. YOLOv11 AIT is a massive catalyst for economic restructuring right now. It's shifting global operations from just reactive monitoring to true proactive automation. In smart cities, advanced driver assistance systems are actively mapping traffic bottlenecks and parking in real time. For public safety, the AI can preemptively forecast a dangerous crowd surge 2 to 5 minutes before it even reaches a critical density threshold. In Industry 4.0, semiconductor manufacturing is using it to detect sub-pixel scratches, saving literally millions in defective chips. In agriculture, it identifies crop diseases to enhance stress resistance, and in ecology, it's mapping those plateau piker burrows with 98.6% precision. Across the board, these systems are operating up to 15 times more efficiently than human inspection. Section 5. Securing Agentic AI Systems, Managing the OWASP Top 10 Risks in 2026. We need to abruptly shift our tone and focus here, because giving vision models autonomous physical agency introduces some terrifying new security vectors. We aren't just worried about a bad output on a screen anymore, we have to account for bad physical outcomes. The OWASP GenAI security project has outlined the top vulnerabilities, and they are critical. Imagine an industrial robot running a YOLOv11 agent. Under ASI-01, an attacker could use a prompt injection, maybe hidden inside a totally normal-looking web page the agent scans, to hijack its goal, basically tricking the machine into ignoring its safety barriers. Under ASI-02, the agent might misuse a legitimate tool, like swinging a sorting arm in a dangerous way. ASI-03 involves the agent abusing cache session tokens, kind of borrowing admin power for unauthorized tasks. And most critically, ASI-05 details unexpected code execution, where these hijacked agents can generate and run malicious code, totally bypassing traditional browser security to trigger a full host-level remote takeover. Which brings us to our final section, Section 6, the ethics of physical AI, navigating regulation and philosophy. So, looking at the global regulatory and moral landscape, how do we actually control a machine that can see, reason, and act all on its own? We have to ground these technical specs in high-stakes reality, especially with the incoming EU AI Act, which gets enforced starting August 2, 2026. Any business deploying YOLOv11-based systems for critical infrastructure or worker management is now dealing with what's legally classified as high-risk AI systems. The era of the black box is completely over. The law now demands auditable glass box architectures with strict logging and built-in human oversight. And if you deploy an autonomous agent that breaks these rules, you aren't just getting a slap on the wrist. Non-compliance carries massive penalties of up to 15 million euros or 3% of your global annual turnover. So the crucial point is that developers are increasingly having to turn to Kantian moral philosophy to navigate what is known in the industry as the responsibility gap, which is the extreme difficulty in assigning moral liability to a machine. Kant's 18th century categorical imperative essentially asks if you would be willing for your algorithmic rule to be applied universally to everyone, including yourself. And surprisingly, that has become the baseline test for AI developers in 2026. It forces developers to ensure that these systems actually maintain human dignity, treating individuals as ends in themselves rather than just data points for operational efficiency. And that leaves us with a hauntingly profound question to end this explainer on. As models like YOLOv11, AEIT grant AI agents incredible physical autonomy, giving them the capability to see the microscopic and reason about the macro, we have a choice to make. Are we building tools of surveillance and control, or are we building genuine extensions of humanity? The technology is already here. The choice of how we wield it, well, that's entirely up to us.